Okay, so with that thought question on chapter 3 lecture, hopefully you have your lecture notes out still, or you pick them back up, put them on your screen. Again, just a reminder, you can minimize my video if you would like. You can still hear my voice and just look at the lecture slides on your screen and just listen. So we're in lecture chapter 3, week 2. This right now we're picking up on slide 32, where we have a thought question. That's where we left off. And in this thought question, the answer to which of the following is not a fundamental difference between the geocentric and sun-centric model of our solar system is the geocentric model is useless for predicting planetary positions in the sky. That is incorrect. It continues to be very useful. Okay? Very, very useful. It's not perfect. That's what models are so great about. Models are models. They're not the reality. They never pretend to be the reality. They're the model citizen is not a real person. Okay? So I use models in my line of work. Model maintenance and repair dollars, the model classroom, the model room for barracks. We don't ever have model. We don't really build the model. We build to something like the model. We always tweak it, but everybody knows what the model looks like. That's what the beauty of models is. Everybody knows what it looks like, and that's what we call standards as well. In slide 34, moving on past the geocentric model, the Islamic scientists, they not only preserved Greek's knowledge, but they also extended it. They built their own house of wisdom in Baghdad in 800 AD. Now I want you to just capture that in your mind. Think about it. 800 AD. I already went through from 18,000 BC all the way to 800 AD. Not much has increased. Not much learning has grown because the Library of Alexandria burned down. Knowledge decreased, monarchs took over, suppressed knowledge, and until 800 AD, when the House of Wisdom started collecting knowledge again, the study of knowledge, pure knowledge, and giving it to the common person, to the folks, to you and me. But then Constantinople, which is just above the Israel, just north of Israel, further north from Alexandria, and northwest of Baghdad. It was 1453 when Constantinople fell in Turkey, Istanbul, Turkey. Now I might have my geography wrong, and you're going to have to prove me wrong or right. But the Eastern scholars headed west to Europe because of that. That spurred on something we call the European Renaissance. So it was the Islamic scientists that got us out of the Dark Ages, if you will. Alright, moving on. So what we've learned so far is that Ptolemy, for example, he tried to explain one of the quandaries of apparent retrograde motion. He tried to explain it, but he couldn't do it very well. And his epiphany, God-given epiphany, was that as the planet Mars, for example, orbits the Earth, it does loop-de-loops. We know that not to be the case, but that was his answer, and God was perfect again. And it wasn't evil, demonic, nothing evil going on up in the heavens. And then that was the Ptolemaic model. We continued to use the geocentric model at this time. Then the Islamists, in slide 36, the Islamic scientists, they took us out of the Dark Ages and the European Renaissance emerged. That's where knowledge was given back to the people. Slide 37. The Copernican revolution was a great time in science history, where Copernicus, he came up with this, he heard about this idea that perhaps the Earth is not the center of the universe. Could it be the sun? Well, the sun may be the center of the universe. Okay, well, he thought maybe that was the case. The problem was he wasn't a very good mathematician, not a very good scientist. He had an idea, he wrote the paper, but the learned scholars of the day laughed at him, scorned him to shame. I mean, they just kind of blew him off, actually. The learned scholars of the day was the Holy Roman Catholic Church, the cardinals, and they just kind of dismissed him. He was a Catholic himself, but he hired somebody named Tycho. He didn't hire Tycho. Tycho, he collaborated with Tycho Brahe, and Tycho Brahe, a man that wanted to prove everybody wrong when he thought he was right, he hired a contractor, just like anybody would do if you didn't know how to do it. Like just recently, I had to put in a load-bearing beam in my house. I didn't do it. I hired somebody that knew what they were doing. Well, Tycho Brahe hired Johannes Kepler, who was a very learned mathematician, and Johannes Kepler was tasked with the idea that the sun was the center of the universe and that the Earth was orbiting the sun. Okay, and Kepler, he had some problems that he had to solve using math. So we're going to talk about how we have 3 laws that emerged from Kepler's work, and how Galileo went farther to solidify that work. We call it the Copernican revolution. Copernicus was looking the Ptolemaic model square in the eye, opposing it. Okay, not intentionally, but that was what was happening. So Copernicus in 1473 to 1543, look how far along, hundreds of years go by, thousands, if not thousands, where he proposed the sun-centered model. It was published in 1543. And he used the same Greek model, but just took Earth out and put the sun in the center. Okay? But it wasn't any more accurate. I mean, objects were still perfectly circular. There was a problem with the orbits. They didn't come out exactly the way they should, time-wise. And slide 39 shows that Tycho Brahe hired Johannes Kepler, and he used observations to discover the truth about the planetary motion. Okay. Now, I told you about apparent retrograde motion and how Ptolemy, through an epiphany, solved that problem. There was another problem that existed that the ancients dismissed, they didn't want to talk about, and it was called stellar parallax. The Earth being not moving, everything else orbiting it, as they looked into the sky, there was a problem. And we're going to talk about that stellar parallax situation. Alright, there was a problem. It seemed like stars were not where they should be each night. Okay, slide 40. Kepler tried to match the observations using the Ptolemaic model, just replacing Earth with the center, with the sun. There was an 8 arc-minute discrepancy. 8 arc-minutes, that's a long time. Well, because of that, he had to create a new math. Next slide shows you how he started working on this new math. And slide 41. Instead of everything orbiting in a perfect circle, which you see on the left, you take a nail and a string and a pencil, you can draw a perfect circle. You've probably done that, right? But you can also take 2 nails, a string, and a pencil and draw an ellipse. Imagine, if you will, taking both nails and putting them together, you get a circle again. Perfect circle. Well, a perfect circle is an ellipse with zero eccentricity. So when you take the two nails, that's a perfect circle, and you start moving them apart from each other, you create more and more and more of a flat, egg-like circle. Is no longer a circle, it's an ellipse. So a perfect circle is an ellipse with zero eccentricity, and then you can make the ellipse more eccentric. If you have a highly eccentric ellipse, the nails are very far apart from each other. Okay? Earth has a moderately eccentric orbit around the Sun. Right? Pluto has a highly eccentric orbit around the Sun. Okay. So with the eccentricity of these ellipses, he started thinking, perhaps the Earth, if the Sun is the center of, they thought, the universe, then the Earth perhaps is orbiting as an ellipse. And maybe all the other planets are orbiting the same Sun in an elliptical fashion. Okay, so slide 43 is that first law. So just think of, let me use street language. Kepler's first law says objects that orbit our Sun orbit elliptically. Okay? They have eccentricity. In other words, the two focus points, or the two nails, are not exactly in the same spot. Not a perfect circle. Okay? As a matter of fact, the Earth is sometimes closer to the Sun than other times. As a matter of fact, when it's farthest away, which does not make sense to you at this point, but when the Earth is farthest away from the Sun, it's a little over 100 million kilometers away. I'm sorry, a little over 100 million miles away. We have summer. And when it's closest to the Sun, about 85, 86 million miles away, we have winter. Now, that may not make sense to you at this point, but we'll get to there in just a minute. But his first law is the Earth orbits in an elliptical fashion. He had a second law that emerged from this. When the Earth, the second law in my language goes this way. When the Earth, as it orbits the Sun, when the Earth is farther and farther and farther away from the Sun, it's moving slower. And when it gets closer and closer and closer to the Sun, it's moving faster. So at the closest point to the Sun, it is moving faster. It says, as a planet moves around its orbit, it sweeps out equal areas in equal times. That's the textbook definition of the second law of Kepler. But my language makes it a lot clearer. What he's saying is you're moving faster when your Earth's moving faster when it's closest to the Sun, and moving slower when it's farthest from the Sun. Speeds up and slows down. Speeds up and slows down. That's the second law. Okay. Moving on to slide 46, Kepler's third law. Kepler's third law. It says, okay, I was just talking about Earth. How about the other planets that orbit the Sun? Well, when you go from Earth to Mars, for example, Earth orbits in 1 year, right? Mars, does it orbit the Sun in the same year? No, it moves slower. That's the reason why we have apparent retrograde motion. So the fact that it moves slower means something. So that is Kepler's third law. As you go from one object to another object farther away from the Sun, farther and farther away, that object, the one that's farther out, moves slower as it orbits the Sun. That's all that Kepler's third law says. But you'll see on slide 46 that it amounts to an equation. In order to write an equation and take in all objects that orbit our sun in the universe, mind you, he had to create a new math. And that math was the first time mathematicians used variables. Instead of just numbers, they used variables. So this math that was created by Kepler, you'll be very, very excited to know that that was created by Kepler. It's called algebra. Are you excited? I hope so. He created algebra. And so you see the equation on the slide. P squared equals A cubed. P being the orbital period in years. A being the average distance from the sun in astronomical units. The unit of measure is extremely important. So if I ask you how long does it take the Earth to go around the sun? 1 year. If I ask you how long does it take Venus to go around the sun, it's going to be less than 1 year. Okay, so we go in years. Mars, longer than a year. Okay, I don't have it off the top of my head, but you get the picture. Now, how far away is Mars from the sun? And I will say it's farther away than Earth in general terms, but in reality it is more than 1 astronomical unit, because the Earth is the only object that orbits the sun that's 1 astronomical unit away. The rest are either more than 1 astronomical unit or less than 1 astronomical unit, but it's all based on astronomical units regarding Kepler's third law, either astronomical units or years. Okay? Moving on to slide 48. He used graphs to prove the point. On the left you'll see that it's amazing, but if you plot the orbits, the p squared in the vertical axis and the a cubed in the horizontal axis of all the planets, the major planets, you'll see that p squared equals a cubed. They all line up. They have a 1-to-1 relationship, meaning p squared really does equal a cubed. It really does equal that. He had proof. And then on the right, the graph on the right, you'll see that the average distance as it compares to the average orbital period. The average distance as it compares to the average orbital speed, meaning Kepler's second law. Mercury's the closest to the sun. And on this chart, Saturn's the farthest away. So Saturn's moving a lot slower than Mercury as it orbits the sun. Okay, slide 49 is the thought question for you. An asteroid orbits the sun at an average distance of 4 astronomical units. How long does it take to orbit the sun? Now you can pause right now, but I'm going to continue and answer the question. The answer is B, Bravo, 8 years. Okay, I have the answer written out. I show my work on slide 50 to give you an idea of how to apply p squared equals a cubed. If you don't understand the way I solved the problem down there, just remember this. If I tell you that an object orbiting the sun is 1,000 astronomical units away from the sun, and I ask you what is its period, what is its orbital period, you should be able to just use Kepler's law, Kepler's third law, to solve that problem. 1,000 astronomical units, that's the letter A. Cube it. 1,000 times 1,000 times 1,000. And then take the square root of that. That is going to be the answer to the question, how many years does it take to orbit the sun? Okay? And if you remember, Sedna is a dwarf planet. I showed it to you in class last week. Sedna is over 500 astronomical units from the sun. What's his orbit? You know? You could figure it out just by using Kepler's third law. So Kepler had 3 laws. Law 1, ellipse. The Earth orbits the Sun in an elliptical fashion. Kepler's second law, as the Earth orbits the Sun, it speeds up and slows down. It's either a little bit farther away or a little bit closer. And when it's farther away, it slows down. And when it's closer to the Sun, it speeds up. Kepler's third law says from one planet to the next planet, the planets that are farther and farther away from the Sun orbit the Sun slower. Takes longer. Okay? Then Galileo came along. Galileo solidified the Copernican revolution in slide 51. Galileo, we're moving along in history. I mean, we're coming up to 1642 here. He overcame some major objectives in the Copernican view. He expanded on Kepler's laws, improved many of it, noting that the Earth and the heavens are not what we would call perfectly circular. That didn't mean anything about God. He noted that Earth really does orbit the Sun, and he had proof of that. Not everything orbits the Sun, though. Other things orbit other things. He was able to prove that. The fact that Earth orbits the Sun leads me to my next thought, is stellar parallax was a problem for the ancients. Meaning, as they looked into the sky, into the heavens, and they saw the stars in June, for example, they saw some stars in one particular location, let's say right there. And then in January, they would look up at the same location in the sky. They would see the star not there, but it would be over there. And it really freaked them out. That's called stellar parallax. What they did not realize is the Earth is 93 million miles from the Sun on the average. So if it's on this side in January, it's on that side in June. 93 million times 2. 186 million miles on the other side of the Sun. That was the problem they had. They didn't know. That's what we call stellar parallax. They didn't know that some stars were close, others were far away. And the close ones were the ones that seemed to be moving. Yeah. So they didn't realize that. So in slide 52, he overcame the first objection. Is Aristotle thought that all objects naturally come to rest. It's not true. Everything's moving. We already talked about that. We're not sitting still. Talked about that last week. Never are sitting still. You do not want to sit still. It is not good. It's not natural. It's not God-given. Galileo showed that objects will stay in motion unless a force acts to slow them down. And that was Newton picked up on that. We'll get to Newton in just a second. So I'm going to go a few more minutes before I go to my next lecture on my last part to this chapter 3 series of lectures. He overcame the second objection about being perfect circles. He used Tycho Brahe's observations of comets and supernovas. So he actually he fabricated his own telescope. He heard about it from the Great Society, not the Great Society, but England had a scientific community, which the Royal Society. They told him about a telescope that you can make, and he started looking at, well, the sun, and he noticed that the sun was dark in spots. There were imperfections, and he called them sunspots. He also looked at the moon and noticed that the moon had mountains and valleys. Then he also looked at Jupiter and Mars. If you go into slide 54, you'll see that Tycho thought he had measured stellar distances. A lack of parallax seemed to rule out an orbiting Earth. But Galileo was able to prove, in part by using his telescope, that he could see the clouds, the Milky Way cloudy stars, countless individual stars, so there's other objects orbiting other things, so he was able to see some stellar parallax in other objects, and that objects must have been farther away than others. They're not all the same distance away. Slide 55, some of his notes taken to prove that Jupiter has moons. Galileo was the first to find the 4 largest moons that orbit Jupiter. So we call them Galilean moons. Those are Ganymede, Io, Callisto, and Europa. We'll talk about those later. Then in slide 56, you'll see that what Galileo did was he said, okay, we have this dilemma. The Holy Roman Catholic Church believes one way. They believe the way Ptolemy, the Ptolemaic model, and it's the prevailing opinion of the world. So I am learning things that contradict that. Okay, so how do I do this without pissing people off? Pardon my French. I'm going to write a book, he said. The dialogue between two worlds. I'm going to compare both. I'm not going to say which one's right. I'm just going to compare, and that is it. On the left, you'll see in slide 56, I'm going to give you the Ptolemaic model. On the right, you'll see on the same slide, I'm going to give you the sun-centered model. Okay? Alright. And I'm going to let anyone else decide. I'm not going to choose sides. I'm not going to fight the Holy Roman Catholic Church. I mean, I'm a Catholic myself, that's what Galileo said. He believed in God, and he believed in the Catholic Church. It was not a question. So if you move on to slide 57, the Catholic Church wanted Galileo to recant his book. I mean, and to ask for forgiveness, and they gave him. They forgave him, but they didn't allow him to live outside the confines of one house. He was under house arrest for the rest of his life, never to see his daughter again. What? Well, what we didn't know until later was that Galileo was a really good friend of the Pope's. They grew up together. And you know how all friends, they always have inside jokes. Well, in Galileo's book, at the end, he wrote a little joke. He jabbed an inside joke at the Pope. The Pope never got his book. The cardinals read his book and wanted him to die for it, for blaspheming the Pope. Well, Galileo was vindicated by the Church in 1992 by Pope John Paul II, saying that everybody's entitled to their opinion. But, you know, the thing is, Galileo was just a friend of the Pope. So, with that in mind, talking about how religion and science they conflict with each other, and sometimes it could cause death. So let me give you this. Psalms 27 verse 1, slide 58. The Lord is my light and my salvation. Whom shall I fear? The Lord is the strength of my life. Of whom shall I be afraid? Galileo, in order to live, he had to recant his book. Even though his book didn't really say anything, it just compared two worlds, if you will. We could live in fear. And Galileo had no intentions of dying. Okay, we should not live in fear. It is a sin, actually. So don't be afraid to express if you disagree with anything that comes out of this class, for example. The fact that I believe in God. You don't have to believe in God. I want you to believe in God, but neither here nor there. God created science. I want you to think of it like that. You don't have to agree, just think of it. Okay, what have we learned? We learned that Copernicus, Tycho, and Kepler challenged the Earth-centered model. And with that Earth-centered model, Copernicus started the motivation to prove it. And we had Kepler's laws as the result. In slide 60, Kepler's laws are summarized right there. Make sure you understand Kepler's laws. Make sure you understand them. We also learned in slide 61 that Galileo went farther. He was able to prove the imperfections. He was able to prove the sun-centered model. Again, the sun being the center of the entire universe. Okay, we're going to take a break, and I'm going to finish up with the last part of chapter 3.